Okay, we're going to start talking about a specific type of chemistry called thermochemistry. Thermochemistry is actually a subset of thermodynamics. Thermodynamics is the study of all the energy relationships in the universe. Okay, it's a very, very big section of concept in physics, both chemistry and physics. Thermochemistry is a subset of thermodynamics. Where we're only really worried about the thermal relationships, all right, involving heat. Thermodynamics, I know the words are very similar, have other aspects besides thermal energy involved, and we'll study those later in the year. We're just worried about that whole thermal energy in thermal chemistry, basically the heat given off or absorbed by chemical reactions. Also, the heat given off or absorbed when there's a temperature change involving something. For this, we're going to use the SI unit, the joule. Okay, joule is our energy unit in this class. It used to be the calorie, okay, but the SI unit took over from the calorie. The calorie is also a thermal energy unit, and when you see that in the back of a candy bar wrapper, the calories, it's actually related to thermochemistry. It's actually the energy given off when they burn that candy bar. So it is an actual chemical reaction that they do, a combustion reaction on your candy bar. And when they find out how much energy is given off, they put it on the wrapper. I've also seen joules on the packages, and it would actually be nice if they started doing it in joules instead of calories, just because the joule is now the modern unit. System and surroundings, this one's pretty easy. Alright, just to get our language on board here in Universal, we're talking about a system being what we're actually talking about, what's being studied. Okay, so if I put my beaker down, my system is what I'm actually looking at. Everything else is the surroundings. Alright, and the surroundings would be everything here, everything here. Also, the cup itself would be the surrounding, the actual container. Can't forget about that. Different types of systems and surroundings. Alright, different types of systems. We have open, closed, and isolated. And I can draw a couple of pictures for these. Basically, that beaker is an open system. What I mean by open is that both thermal energy can go in and out of the system. Also, matter itself, like maybe evaporation, can leave the beaker or come in from the surroundings and go inside the beaker. So that's an open system. A closed system would be the same thing. Okay, same exact thing, but put a lid on it. So when you put that lid on, you still have thermal energy going in and out, but you don't have matter itself. So the closed system energy can go in and out, but not matter. And then lastly, we have something like an isolated system, and for that, I'll draw my poor man thermos. Okay, a thermos is basically a container in a container. So now, instead of a beaker, I'm using my thermos. My system is isolated from the universe, okay, the surroundings. And now I have a cap on it, so there's no matter escaping or gaining. And because a thermos has a very, very good insulator here, it's actually a vacuum, I do not get that interchange of the double arrows of heat, okay, thermal energy going in and out. A very good thermos can actually keep coffee hot for in upwards of 24 hours. Okay, so they do a really good job. It's not a perfect system. If it was perfect, the coffee would stay hot indefinitely. It's not perfect, but they do a pretty good job. So that would be a good analogy of an isolated system. In our actual heat, what we're talking about, is thermal energy, and it goes from a substance of higher kinetic energy to lower. What I'm actually talking about here, okay, in common day verbiage would be that our thermal energy always goes from hot to cold. Okay, if something, there is no such thing as cold energy. Okay, if something gets colder, it gets colder because it warmed something up. All right, what I mean by that is if you get into the bathtub and it's hot, okay, and after 15 minutes the water gets cool, the water got cool because it warmed up the bathtub, the air, and you. And now the water is not warm anymore. It transferred all of its energy. Another analogy is maybe if you leave the window open in a winter day. Okay, you're not letting the cold in. Okay, this is assuming there's no wind. You're not letting the cold in, you're letting the heat out. And when the heat leaves your room and goes out to warm up the air outside, then the actual room gets colder, okay, because you lost energy. So it always goes in the direction of hot to cold. It's an easy way to track it. There's first law of thermodynamics. For those of us that have had physics, this should be familiar. It's conservation of energy. Okay, energy is conserved in a chemical reaction. Conserved meaning you can track it. It's not created or destroyed. And we're basically talking about we're tracking the energy going in and out of the system and the surroundings. Okay, so that's our observation, is basically seeing the change in energy. And what I mean by that is it doesn't matter how you actually got to that state. Okay, it's the here and now. For example, if something gets warmed up, okay, from where it started at energy 1, okay, thermal energy 1, to where it's actually at, all right, at thermal energy 2, that according to this whole idea of state function, it wouldn't matter that, the history of this would be it was warmed on the stove and then warmed in the oven. All right, so it wouldn't matter how it achieved this energy. Okay, doesn't matter the actual pathway. Okay, whether it was in the oven and the stove, doesn't matter. It's that it's achieved this new degree of energy. So it's more of a here and now, not a pathway dependent. And the only reason we're really going over this is it does show up from time to time in the multiple choice questions. Okay, so things like phases, temperature, pressure, okay, those are all state functions. Enthalpy, okay, our H, is our thermal energy, our heat energy that we're talking about. All right, it's unmeasurable as H. It cannot be measured as H. We can only measure the change. Okay, we can never get the amplitude of what H is. We can only measure, okay, delta H, delta meaning change. So we can only measure the change in heat. Okay, we can't just measure heat at a snapshot. All right, and if we're talking about constant pressure, our delta H is also equal to Q. Okay, the little p means constant pressure. We have this new equation here. Delta H equals delta energy plus P times change in volume. All right. This is given on our equation sheet. We don't really need to reference it. Doesn't really come up. But enthalpy itself is a state function. Okay, so again, back to state functions. It means that the heat given off or absorbed doesn't really matter how it actually came about. We're only looking for the actual amplitude. Okay, so we're not looking for the storyline, just the before and after effects. All right. Enthalpy of reactions. All right, it's basically the change in heat of the products minus the reactants. Okay, that would be our delta H, or the enthalpy of reaction. Um, Again, and delta H would be equal Q at a constant pressure. Exothermic reactions are negative delta H. Endothermic are positive. And for those of you that don't remember, exothermic meant that heat was leaving the system to the surroundings. Okay, so if I go back to my beaker, exothermic meant that thermal energy is escaping. All right, so this is exo. Endo meant that thermal energy is being absorbed. Okay, so when you're leaving, when your energy is leaving, it's exo and it's a negative sign. When it's endothermic, it's being absorbed, it'd be a positive sign. And we actually have a little bit of information here of making our water H2 plus O2 yielding H2O, and we have an actual measure of the thermal energy, okay, associated with that. Enthalpy and stoichiometry. Okay, it's a relatively simplistic. It's basically, again, here's our reaction, our delta H of this reaction of building our water up. And it's assumed that when 2 moles of H2 are consumed or reacted, that negative 483.6 kilojoules are released. Okay, it's a little redundant to say released and negative, because remember, exothermic means released, so the negative is already saying that. It's just the way the vocabulary works out that you end up saying the same thing twice. And what we actually mean about the stoichiometry, we could also make up maybe a question saying how much energy is changed over from using 5 grams of H2. And to do that, you would get to 1 mole of H2 is 2 grams of H2. And using this negative 483.6 kilojoules, which is basically per the reaction. And our reaction with respect to H2 is that there are 2 moles of H2 in the reaction and negative 483.6 kilojoules of heat are evolved. So you could crunch these numbers to actually get the actual value, but this is a example of thermal stoichiometry. The key thing to know is that this actual value here is per reaction. Okay, and all I'm saying to that, it's per mole of any reactant or product. So with respect to H2, you would put a 2 here. Now if I said 5 grams of water, okay, we could change these all to oxygens. 1 mole of oxygen is 32 grams. And if I change this to oxygen, I would have to change this value to 1. Okay, because the coefficient 1 would have to be in there, because again, it's negative 483.6 kilojoules per reaction. And when we do our reaction, we only have 1 mole of O2 instead of 2. So basically, you're doing the delta H over the mole of coefficient, the coefficient mole on the bottom. And these tend to be somewhat simplistic calculations. PowerPoint issue here. Alright, something that we may have never covered is that enthalpy, whether you're going forward or reverse, okay, in your actual reaction, the actual enthalpy is the same. The difference is the sign. So for example, if I was going to break open my water, back into my H2 plus O2, I don't have to look it up. I know that this delta H is a positive 483 kilojoules. How do I know that? Well, I remember in the last slide it was negative 483 kilojoules. So an exothermic reaction. So the reverse would be the same amplitude. It would just be positive or endothermic instead. And it should make sense that it would actually have to absorb energy in order to break down my water into its parts. Also, enthalpy depends on the state of the reactions and products. So what I'm saying for that is that 483 was only for particular states. Okay, so it matters if I'm breaking down my water from a liquid or if I was breaking down my water, okay, from a gaseous phase. Okay, if I was doing it in another phase, the value would not be, would most likely not be 483. Okay, because the actual phases do matter. And I believe the last one was with the gases. Okay, the reaction was with the gases, so this would be the 483 kilojoules. This delta H, I would actually have to look up because I don't know, because doing it in a different phase changes everything, because the state does. Okay, the state of the actual reactants and products are very important. Calorimetry. Calorimetry is just the heat flow in a system. Basically, we're looking to warm something up or cool something down. All right, calorimetry is usually used in a styrofoam cup, okay, with some water in it. And I could warm up maybe a gold ring. All right, my AU ring, it's a golden ring, and put it in the water and study what actually occurs to the water. Okay, how much my water actually warms up or cools down. And I can develop some characteristics or relationships on how my gold, properties on my gold or properties in the water. Okay, what I mean by that is we're basically studying how easy or hard it is to warm something up or to cool something down. And that's coming up in a second. Our reaction here for delta H is, again, we did this before, the change in energy plus P delta V, okay, change in volume. This was at constant pressure. But if no gas is being involved, the P delta V is actually essentially 0. So the actual change in energy is actually just the thermal energy. Okay, in layman's terms, what am I talking about here? It sounds really confusing. I'm basically saying that the energy given off, okay, the energy given off by my ring or my copper penny, okay, here's my copper penny, here's my coffee cup. The energy given off from me warming up my copper penny and putting it into the water is only going to be thermal energy. I don't have to worry about this P delta V. The only reason I would have to worry about that would be maybe if I got my copper penny almost to a molten state where the water would boil off. Then it would be important to actually pay attention to the pressure volume characteristics. But if no gas is being involved, no steam or any reactant gas is being involved, we're just warming and cooling something down in essence. So the energy of the system change would be the same as just the thermal energy. All right, here's our beautiful equation. Okay, Q equals MC delta T. Q equals MCAT. C is the specific heat. Okay, C is the specific heat, and that's basically how hard or easy it is to cool something down. Basically, we're talking about the amount of energy to raise or lower a degree for the substance. Okay, how much substance? 1 gram of substance. So specific heat was the amount of energy in order to warm or cool an object, 1 gram of substance, 1 degree. But in essence, we're just talking about how easy or hard it is to cool or warm something up. Q is heat, M is mass, and delta T is temperature change. Okay, note that that can actually be in kelvins or Celsius, and the reason for that is because the amplitude between each degree is the same whether you're in the Celsius or the Kelvin scale. We have the specific heat of aluminum being 0.9. All right, many of you already know that the C for H2O liquid water, okay, it matters that it's a liquid, is 4.184. Again, that's the energy per gram per degree Celsius or Kelvin. Okay, so it's the water is extremely hard to change its temperature. So you have a number of basically 4.2 over 4 times harder to change water's temperature per gram per 1 degree Celsius compared to that of aluminum. Aluminum's temperature is relatively easy, okay, to change. And when I say easy to change, I mean that you don't have to add all that much heat to it when compared to water. Okay, water would take over 4 times as much energy. All right, here's a easy practice problem. If you remember, the C for aluminum was 0.9. Okay, for C for Al was 0.90 joules per gram degrees Celsius. And my question is, how much heat is needed to raise 10 grams of aluminum from 22 degrees to 42 degrees? Well, Q equals MC delta T. There's my M. Here's my C. Okay, that's a J. And my delta T is 20 degrees Celsius. It was actually 20.0. This would be a pretty good multiple choice question. Hopefully you can see that 10 times 0.9 is 9. 9 times 20 is 180. 180 joules, because Celsius cancel out with Celsius. I'm sorry. Grams cancel out with grams. And we're left with the joule. Okay, so it's joules, it's not kilojoules. So we're looking for 180. Like I said, that's a good multiple choice question. Note that if you're going into kilojoules, that'd be 0.180 kJ. Constant pressure calorimetry. Okay, constant pressure once again just means that there's no, it's not contained. Okay, so we're talking about a system where there is no change in volume because it doesn't really matter. All right, I'm talking about our empty styrofoam cup, okay, with some water in it. All right, the assumption is that the heat remains in there, but it's a pretty good system, but obviously it has many shortcomings. It's not nearly an isolated system. All right, and if we do these in water, and we're actually not just warming up a copper penny and throwing in it, or a gold ring, and we're actually doing reactions, we're assuming that the heat gained or lost by the reaction is the opposite of the heat gained or lost from the water. What I mean by that is, if I actually run a reaction in my water here, a common reaction would be maybe HCl plus NaOH. Okay, HCl plus NaOH gives off a lot of heat. So if I do this in my water, all right, the water is going to warm up. And I can take the opposite of that heat and know the heat for my reaction, because it should be exothermic, it will be negative. And if I do my water calculation, when the water temperature increases, I will get a positive Q value, but my reaction value will actually be the opposite. And we'll see some problems that are related to this. All right. Silver nitrate and HCl. All right, when you're adding 50 mils of 0.01 molar silver nitrate to 50 mils of 0.01 molar HCl at constant pressure calorimetry, the temperature increases from 22.3 to 23.11. Okay, calculate the H on a molar basis for the reaction. Okay. Well, first assumption is, the first assumption is, what are we actually talking about? We're talking about water, and we're assuming that the solution being 100 mLs, okay, we're assuming that my 100 mLs of solution is 100 mLs of water, all right, which isn't technically true, but it's a pretty safe assumption nonetheless. So my 100 mLs of total solution translate into 100 grams for the water. Okay, not true, but it's an assumption that's always made. Also, we're going to assume that my specific heat of the solution is 4.18. Okay, that's also not true, but it is a pretty good assumption to make. What I mean by that is it's not true because we're not dealing with pure water anymore, but the numbers are going to remain. All right, so in order to actually figure out how much heat is evolved during this reaction, all I have to do is just analyze water's values. All right, and if I analyze water's values, I get Q equals 100, okay, times 4.184. All right. And what do we have here? 0.7, 0.81, 0.81 degrees Celsius. All right, this will be the actual Q for the water. Now, the delta H for the reaction, and first of all, please note that my final minus initial, because we warmed up, is going to be positive. My delta H for the reaction is going to be a negative Q. Okay, and it's also going to be divided by however many moles I have, which would be 0.05. Well, I should really start with the reaction here. We're dealing with AgNO3 plus HCl. And they react in a pure double replacement to AgCl and HNO3. Okay, everything is 1-to-1, so I'm just looking for 1 mole. Okay, so I find my Q of the water. My delta H for reaction is actually going to be the overall Q divided by however many moles I have. Okay, and I'm dealing with 1 mole in the reaction, so I'm just going to find out how many moles I actually have right now. And I have my 50 mils, which is 0.05, times my molarity, which is 0.01. Okay, so calculating delta H on a molar basis for this reaction would be this Q. I'm sorry, I don't have my calculator. This Q divided by that many moles. And note it's the opposite. Why? Again, because the water goes positive because it's absorbing heat. It's getting heat from the reaction, which is exothermic, and it gets that negative sign. And you could do the math on that and see exactly what number we're talking about there. Now the opposite is of a constant pressure calorimeter. All right, is actually a constant volume calorimeter. And a constant volume is kind of hard to do. You have to have a well-armored vessel, okay, like a pressure cooker. We call those a bomb calorimeter. All right, and usually these are done for combustion reactions, okay, where you actually can react and keep the volume the same and basically force your growing volume into purely thermal characteristics. What I'm saying by that is if you don't let your volume expand, then you're getting an increase in pressure, and the increase in pressure is actually an increase in temperature. We have this whole concept of the heat capacity of the calorimeter of the bomb must be calibrated very precisely. Okay, and what that is, okay, it's how easy or hard it is to warm up or cool down the actual piece of equipment that you're dealing with. Okay, so each bomb would have a different rating. Okay, so these are different calculations. These are actually very easy calculations, and what I'm worried about basically is the rating of what they call the heat capacity. Okay, and the heat capacity for your bomb will be a joule or kilojoule, I'll say kilojoules, per degree. Okay, note that there is no gram. It doesn't matter what the gram is. We're dealing with the actual instrument itself. And I'm going to leave it like that, and I think it should be clear when we actually hit a couple of sample problems coming up. Note that if volume is constant, then again, we're dealing with our change in energy being heat. We already talked about what will happen to temperature if gas cannot expand and do work on the surroundings. If it doesn't expand, we're basically forcing the hand here of our expanding gas and forcing it into a temperature thermal roll. P delta V is fairly difficult to track, okay, to measure. So we want to force the hand of the reaction that involves a gas and make it so it involves purely thermal energy. And the delta H of reaction for this will be the heat capacity of the bomb calorimeter times the delta T. Okay, remember the heat capacity was a joule or kilojoules per degree Celsius times degrees Celsius. Okay, that's our delta H. Doesn't matter what the stuff is. You have a rating on the actual bomb, which is like a pressure cooker. So when you run your reaction, you're going off that sticker or whatever's engraved on the bomb, and you can just tell how much energy was evolved in that reaction based on the temperature increase alone. Okay, like I said, it's a bit easier because there's not as many measurements to be made. Okay, it's just purely multiplication. Just the temperature is the only measure. Bit of a huge lecture supplement here. Methylhydrazine is commonly used as a liquid rocket fuel. The combustion of methylhydrazine with oxygen produces N2CO2 and H2O liquid. When 4 grams of methylhydrazine is combusted in a bomb calorimeter, the temperature changes from 25 to 39.5 degrees Celsius. In a separate experiment, the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. What is the heat of reaction for the combustion of a mole of hydrazine in this calorimeter? Okay, I'm sorry, methylhydrazine in this calorimeter. Well, the delta H, okay, the delta H that we're dealing with here is the bomb calorimeter value times the change, the delta temperature. 39.5 minus 25 gets me to 14.9. I'm sorry, 14.5. Degrees Celsius cancel out, and can barely see my point. Okay, so when you multiply these two numbers, you're going to get a delta H for the actual reaction of what occurred. They're making it a little bit more difficult by asking per mole for a mole. So you want to take this value, okay, this actual value, and divide it. Perhaps I should actually change this up a little bit and say this is the Q. Okay, if this is the heat, then my actual enthalpy per reaction will be that value, 7.794 times 14.5. Okay, and those are in kilojoules. And it's actually going to be per mole, so I'm going to say 4 grams. All right, and divide that to get it into moles of 28, 30, 40, 46. Okay, now I'm doing the molar mass of CH6N2. Okay, so it'd be the heat, the kilojoules per mole, and that would actually be our work for that massive paragraph. It wasn't very difficult, actually. So it's the actual energy or the actual heat given off by that reaction, and they wanted it per mole, so I divided it by the moles that actually reacted. A lot of problems we're actually trying to find out the heat capacity of the calorimeter. Okay, like I said, most times that's actually a known value, but in this question they're asking for it. Let's read it real quick. Under constant volume conditions, the heat combustion of benzoic acid is 26.38 kilojoules per gram. 1.20 gram sample of benzoic acid is burned in a bomb calorimeter. The temperature change increases from 22.45 to 26.10. What is the total heat capacity of the calorimeter? All right. Well, it's going to be the actual heat capacity, okay, or let's just write heat capacity is equal to the kilojoules. All right, the kilojoules is going to be the mass of the benzoic acid that reacts, and times the actual delta H reaction. Okay, note that they were nice enough to give it to us in 26.38 kilojoules per gram instead of per mole, because that saves us calculations. Okay, it would actually be a little bit harder to do if they gave it to us per mole. Okay, so that's the energy given off by the benzoic acid, and the temperature changes. It looks like 3.75. All right, so we go up 3.65 degrees. So that's our delta. That's going to be our C. So our heat capacity will actually be this value. I'm a little apologetic because I don't have my calculator on me. 1.2 times 26. I'm assuming it's going to be one of these top two answers just by doing some mental math. Okay, 1.2 times 26 in my head, I see that as close to 30, and then I'm going to be dividing this 30 by 3.65. All right, so it's going to be, if it was 3, almost 30 divided by 3 would be 10, but I'm dividing by a bigger number, so it's going to be one of these top two answers. Okay, it's not so bad. These bomb problems are actually, they're somewhat rare, but when we do get them, we like them because they're a little bit on the easier side.